One of the very last things we left off with in the previous unit of study was the behavior of the damped oscillator circuit. And it went something like this. If you have a capacitor, an inductor, and a resistor that are connected on a loop with the two-way switch, and you throw the switch into position A, then you can momentarily charge up the capacitor, and the capacitor should reach a voltage that matches the EMF of the external source. Once the capacitor is saturated, then you throw the switch into position B, and as you know, the result is an oscillation of electrical energy stored in the electric field of the capacitor, and as it discharges and the current grows, then the energy associated with the electric field becomes energy associated with the magnetic field of the inductor, and this goes back and forth. The behavior of the resistor is to act in a non-conservative way and waste away the energy as is being transformed between the energy of the electric field and magnetic field. And so the end result, if we were to graph the current that flows in the circuit versus time, it would oscillate and eventually fade away and decay to nothing. The bounds of the maximum and minimum are decaying away in time, but you can see this oscillatory behavior. Okay, well, let's think of a different combination of inductor, resistor, and capacitor as our gateway into the new unit of study on AC electricity. So what if we put the inductor, resistor, and capacitor all in series and connected that with a battery? Well, how about this? What if we ignored the inductor and made the connection? I think we've reviewed this in a previous unit of study, and the capacitor has a way of causing the current to fade away and decay to zero. Eventually the capacitor gets fully charged and no more current flows. Initially, the capacitor offers no resistance to the flow of electricity. So a graph of current versus time would suggest the initial current is just given by Ohm's law, divide the EMF by the resistance, and as the capacitor fills up, the current fades away and ultimately reaches zero once the capacitor can't hold any more charge. Or how about this? What if we ignored the capacitor? And so we had an inductor and a resistor in series. So that also has a graph of current versus time that's non-uniform. In this case, the same value given by Ohm's law, dividing the EMF by the resistance, is a meaningful value, but the idea of an inductor is that it acts sort of like an electrical form of inertia, and it doesn't allow the current to immediately reach that value. The current grows and approaches that value asymptotically. So it should make sense that if we were to put all three of them together and connect to a source of DC like a battery, okay, so in all of these cases, the EMF we're picturing will provide a source of DC, then it stands to reason the inductor is going to limit the rate at which the current can approach the value given by EMF over R, and the capacitor is going to ensure that the current doesn't remain forever. So, due to the existence of the inductor in the circuit, the current approaches E over R, but due to the capacitor, it starts to fade away in time, and so it's likely the current never reaches its peak value before it dies off and fades away towards zero. Well, this really is not a practical circuit, and you won't find circuits of this type very often. You will find circuits that put an inductor, resistor, and a capacitor together in series, but not if they're connected to a source of DC. If we put a label here, say this is a generator, maybe we'll use a symbol like this. Well, we can't really label it like we do DC as positive and negative. The whole nature of a generator is that the polarity is constantly cycling from positive to negative. And so instead of a current flowing in one particular direction through the circuit all the time, the current flows clockwise and then comes back counterclockwise, and the generator forces an oscillating current through the circuit. Now what's the graph of current versus time going to look like? So that's the emphasis of this unit 5.2 on the study of AC electricity and AC circuits. And so I would encourage you to stay tuned and find out what exactly is the behavior of such a circuit. First, let's do a review of the way in which generators operate.